So welcome to my presentation. Yeah, you already gave a bio of myself. So I'm currently a postdoc in Jim Rolling's group in Madison, and I will stay here until summer next year. So if there are ideas of what I should do afterwards, then just email me some promotion. All right. So I'm going to start by talking a little bit about methods for numerical optimal control in general, and how CasADi, the framework that I will introduce, fits into this. All right. So we are interested in optimal control problems in general. So in optimal control, we're trying to solve some optimization problem. Typically, we have a cost function consisting of some integral term and some end cost term. And importantly, we have, like, as constraints in our optimization problem, we have an ordinary or differential algebraic system of equations. So here is like one simple example of optimal control problem, trying to minimize this cost function here, and we have bounds on our states, on our free controls, and free parameters in this case. All right. We are interested in this both in the open loop case and in the closed loop case. So this is so in the closed loop case, we're talking about volume predictive control. So typically, what we do is that we solve this problem in a loop, and then we feed back the optimal solution at the initial time to the system, and then we keep resolving this problem. So this is in the closed loop case. All right. So now, I showed you a very simple example of an optimal control problem with just a very simple or very standard explicit ODE. But in real life, problems tend to get much more complex than this. So instead of an ODE here, we can have a differential algebraic equation in DAE. We might even have a PDE. I've been working a bit with problems with periodicity constraints, where we have we're looking for periodic solutions. We might have multiple objectives, looking for example, a Pareto front. Multi-stage formulations are important. There are stochastic, robust, mixed integer formulations. So the reason why I'm bringing you this up is that we need a flexible approach to be able to handle a wide range of different optimal control problems formulations. So this is what I'm trying to address in this work. Okay, so that's for the formulations. So for the methods, the type of methods that are, let's say, the state of the art for solving this type of problems are so-called direct methods. So in direct methods, which are also referred to as discrete-time and optimize, we are looking at, like, so as a first step, we are replacing our infinite dimensional free control trajectory with a parameterization. And in the simplest case, you're choosing, for example, a piecewise constant trajectory. So, and this allows us to reformulate this optimal control problem into a finite dimensional nonlinear program. And so the reason why you want to do that is that there are a lot of good methods for solving nonlinear programs. But you can do this in different ways, and depending on how you do this transcription from nonlinear program to, from optimal control problem to nonlinear program, you get different performance in terms of solvability and how well it scales to large dimensions. And I'm just going to mention three methods that are popular. So it's direct single shooting, direct multiple shooting, and direct collocation. So these are three methods that are popular in real life or real world applications. So in the direct single shooting method, what we essentially do is that we introduce an ODE solver. So think of MATLAB's ODE 4.5 or 15S or whatever, and we use this to, and like introducing this in our optimization formulation allows us to eliminate the state trajectory. So we're going from a a continuous time problem to a discrete time problem, where we only have our free parameters and our set of our control parameterization. And in our control formulation, we have this called this ODE integrator that allows us to eliminate the state trajectory. So this is like an algorithm here. So, so what does this NLP look like? Well, we have these embedded integrators in our problem formulation. So we need to be able to, just to formulate our problems, we need to be able to solve these initial value problems in ODEs or DAs. This is a nonlinear program.
Okay, now I have connection, huh?
Yes, you have connection. All right. Okay, so okay, so we solve this with a gradient-based methods, and the two popular families of gradient-based nonlinear programming methods are SQP methods and interior point methods. And in this case, both these cases, we need first and preferably second-order derivatives. So we have these. We need second-order derivatives with these embedded integrators. So there are a lot to be said about single shooting. There are a lot of problems with it, and one of the problems is that you might not even be able to evaluate this x value, the state trajectory for a given guess of u. So this is not a very suitable method if you, for example, have an unstable system. And there are other problems, such as difficulty to parallelize. So that's one of the reasons why we are looking at other methods. Another popular method is the direct single shooting approach. So in the direct single shooting, in addition to our controlled parameterization, we also let our state trajectory be a decision variable in the nonlinear program. So if you look taking our single shooting NLP, if we lift this to a higher dimension and include our state trajectory here, x1, x0, x1, and so on, into our NLP formulation, we get a higher dimensional problem. So we lift the problem into an equivalent higher dimensional problem that we can solve instead. So we end up with a larger problem. So these we have these additional variables in our NLP, and we have these additional constraints. So the state trajectory continuity constraints are now enforced by the optimizer instead of being just eliminated. So we have a large NLP, but it's structured, and there's a structure we can exploit there. Importantly, we also get we're able to make use of initial guesses if we have them for not only the U trajectory, but the state trajectory as well. And there are other advantages of this approach. One is that in this higher dimension, it often converges faster to the optimal solution. And there are, I'm not sure if it's completely understood why. I mean, you can explain, but there's in this paper here, the Albers-Myers and Deal paper here, there are some pointers to why this might be the case. But it's in some sense, it's a less nonlinear program in its higher dimension. All right. So another advantage of this formulation is that now all these integrator calls that are typically very expensive can be evaluated in parallel. So that's another reason to use it. Right. So how do we solve this problem? So the state of the art is to write customized or tailored structure exploiting SQP methods for this, or structure exploiting gradient-based methods. All right. So that's direct multiple shooting. The third the method I want to mention, just very briefly, is direct collocation methods. So in direct single shooting, direct multiple shooting, we had these embedded integrators, and there are different ways to evaluate these to get to numerically, so say, solve your initial value problem. One way we can do this is to use collocation methods, and collocation method is a type of implicit Runge-Kutta method. So we can use that in the context of direct single shooting or direct multiple shooting. But what we can also do is that we can inline this collocation scheme into our NLP formulation. So so basically we take the whole integrator and we include that in our NLP formulation. So this means this allows us to replace our objective with some sort of quadrature formula, and it allows us to replace our discrete-time dynamics with an implicit system of equations. So if you want to, this is just a very simple sketch. So it's explained very well in Larry Bigler's book, Nonlinear Programming. So I would recommend that as a reference. Well, anyway, so what do we have? In direct location, we have an even larger NLP, but it's in this case, it's not only block sparse, it's actually typically very sparse. We no longer have embedded integrators, which is convenient. But there are other issues. For example, you need to be able, you need to make sure that you choose a suitable time dispensation. You end up with a very large problem. So you need to solve. You need to be careful in how you solve the NLP. Like direct multiple shooting, it's very easy to parallelize. And there are good methods for solving this based on sparsity exploiting grained methods, and that are implemented in software framework like IPOpt. And like direct multiple shooting, you can also make use of initial guesses for both your state and U trajectories. Because it's in a high dimension, you also get fast local convergence, similar to what you have in direct multiple shooting. So those are the kind of methods that we want to be able to implement. So what is CasADi? So CasADi is an open source, freely available optimal control framework for numerical optimization. So, and the main purpose of CasADi is to facilitate this transcription of optimal control problems to nonlinear programming problems. And we try to facilitate this by providing high-level building blocks to make this transcription as smooth as possible, and allow you to implement efficient optimal control methods in, say, 100 lines of code instead of 10,000 lines of code, which is transformative. All right, so CasADi has been around for a while now. It's almost 8 years ago since I started working on this, and so it was the original motivation was to try to find a way of solving optimal control problems with a model came from Modelica. Modelica is this physical modeling language. But after that, it has, so to say, got a much broader scope. And so CasADi was, okay, so started 8 years ago by me, and then 2 other grad students joined very early on in the project. So Joris Gillis and Greg Horn. And especially me and Joris, we have been working on this essentially from the very beginning, and we are, so to say, still the developers of the project. So it's a small and consistent development core of CasADi. So CasADi, since its inception, has been used in a lot of projects. I think sometimes I look at Google Scholar to see how many people have cited us. So it's somewhere in the order of 300 citations now for different types of applications. And this is both in academic research, in teaching. So we've been using CasADi to teach optimal control, and also in several industrial projects. And just today, actually, we released version 3.3 of CasADi. So it's available for downloading right now. All right. So what is CasADi? So CasADi in the core of CasADi consists of a symbolic framework. So you think of something like Symbolic toolbox for MATLAB. And the key component of this symbolic framework is an efficient implementation of algorithmic differentiation. So algorithmic differentiation is a technique to analytically and efficiently calculate derivatives. So the AD framework in CasADi is a so-called source code transformation type AD framework. This means that we build up symbolic expression graphs, and then we apply the framework to the expression graphs, building up new expression graphs corresponding to the derivatives. These expression graphs in CasADi, they importantly support high-level operations. So this means matrix operations, but it also means things like backslash operations, if you think MATLAB, or root finding solvers, or ODE integrators. So these are things you can algorithmically differentiate in CasADi. This AD framework, the AD in CasADi can then be used for a number of different things. One thing that it's being used for is to calculate derivatives for gradient-based optimization. But it's also used for a lot of other things. We use it to implement implicit integrator schemes. So in our interfaces to solvers. We use it for things like sensitivity analysis, for index reductions of DAEs, or you can use it also for things like robust optimization. So that's like the core of CasADi. And around this core, we have, just like modeling frameworks you're maybe familiar with, like AMPLE or GANS or Julia Jump, we have a set of interfaces to nonlinear solvers, or to other numerical solvers. And this includes NLP solvers, some of them supporting discrete variables. We have interfaces to convex solvers, in particular QP solvers, and we have interfaces to some solvers for initial value problems in ordinary or differential algebraic equations. So we have the core, we have the interface around it, and then we have these different interfaces, so different front ends. CasADi itself and all the interfaces and everything is written in C++. It's self-contained C++, no external dependencies. But most people don't use CasADi from C++. They use it from a higher level interface, in particular via Python or MATLAB Octave. And because all the computationally expensive things go on in the low-level Symbolic framework and so on, it doesn't really matter from an efficiency point of view which front end you're using. All right. One important feature of this Symbolic framework, something that we've been working a lot on the last couple of years, that has been pushed by industrial applications, is the ability to generate C code from these symbolic expressions. So this C code is not necessarily very readable, but it's self-contained C code without any dynamic binary allocation. So it's code that can be used, can be compiled on almost any system. Why do we do this? Well, one reason to generate C code is that it allows us to speed up computations, and we do this. I mean, you can compile the code yourself, but we also distribute CasADi with a just-in-time compiler based on LLVM Clang. It also allows us to port code, so we can do modeling in, say, MATLAB or Python on one computer, and then we can export the code and run it on an embedded system. And finally, the C code export allows introspection. So the C code is essentially like a snapshot of what goes on in CasADi's virtual machines. So it allows you to have a look essentially at the symbolic expressions, and even things that cannot actually be compiled, you can still generate C code and to get an idea of what you're actually calculating. All right, so I'm going to make a little small a demo to just give you an idea if you haven't seen CasADi before. So here is like a simple optimal control problem. We're trying to minimize. We have an integral over, let's say, 10 seconds, and we're trying to penalize the square deviation from the origin, and we have this quadratic penalty of the control effort. We have a very trivial DAE with two states and one algebraic state, and with bounds on our control and state. So what CasADi allows you to do is to take a problem like this, or a much more complex problem than this, and to implement your own control method easily. And here I'm going to show how you implement methods such as direct multiple shooting, with exact second derivatives calculated via automatic sensitivity analysis, and then solved using an NLP solver code. All right. So how do you do this in CasADi? So this is CasADi in MATLAB or Octave. So typically what you do is that you start by creating symbolic expressions for your variables. So in this case, we're creating 3 symbolic variables for our state, our algebraic, and our control. And then we're using this to build up new symbolic expressions for our ODE right-hand side, our algebraic right-hand side, and our objective function. So what you can see here is that you see the similarity with Symbolic toolbox in that, yeah, you're basically just creating symbols. And just like in Symbolic toolbox, everything in CasADi is a matrix. So we don't have like scalars and vectors. It's all matrices, and a vector or a scalar is in fact just a 1-by-1 matrix in CasADi. And this is true whether you're using CasADi from MATLAB or Python or C++. In fact, everything is a sparse matrix. So we only have one type of expressions, and it's a sparse matrix. And this is actually different from Symbolic toolbox, because Symbolic toolbox matrices can never be sparse. They always don't. All right. Okay. So we have these symbolic expressions for our continuous time dynamics, and then we're typically using an interface to formulate our discrete time dynamics. And here we're going to do it using IDAS from the SunDice suite. And it's really quite easy to use, because the interfaces are built on the symbolic. So all you need to do is to pass these symbols, the symbolic expressions, into the constructor of the integrator class. And because it's symbols, and because CasADi has like ways of calculating derivatives, the interface will generate all the needed expressions, or all the needed like things like Jacobian of the right-hand side, and so on, that could be needed by the solver. So the SunDice solvers in this case has full information. So everything that the solver code could possibly ask for is automatically generated by the solver. So this, in this case, we get with this piece of code, what we're essentially doing is that we're creating this mapping function from current state and our parameterized control to state at a later point, and also like the contribution to the cost function. Okay, so we have our discrete time dynamics, and then we simply build up a new expressions for our NLP. And the way you typically do that is you start with an empty list of variables and constraints, and then you step by step just add them to our structures. And so this is going to create a new symbolic expression which contains function calls. So F here is our discrete time dynamics. It will create like an expression of function calls to our ODE, our ODE solver. So at the end of this, we're getting symbolic expressions for essentially J and G here. All right, and finally, with these symbolic expressions for our NLP, we throw it at the NLP solver, and this gives us an object that we can actually evaluate and solve. And again, because we have these symbolic expressions for our NLP formulation, CasADi is able to automatically generate all the derivatives needed by the NLP solver in this case. All right. So here's a whole line of code. Like this is 50 lines of code that allows you to implement direct multiple shooting, in this case with first and second order derivatives, with very little, hands-on you don't need to worry about providing sundials, for example, with the right derivatives. All right, so that's like just a general introduction to CasADi. A common question in CasADi, I mean, once you try to start using CasADi for non-trivial function is, well, so in this user problem I have here, in the problem I'm looking at, I have this particular construct. Can CasADi handle this construct? And so CasADi being the symbolic framework, it works by breaking down complex functions into sequences of simpler atomic operations. And it's often a non-trivial operation to extend this into like extend this set, because you need the solving. So the symbolic framework needs to know a lot more than just being able to evaluate something in order to embed it into a symbolic framework. So in CasADi, in order to extend this set of operations, you need first of all, you need to be able to evaluate it, but you also need a chain rule. So typically, this means that you need a way of giving this function. You need a way to calculate like a Jacobi times vector product from the left and or from the right, or possibly a way of calculating the Jacobian. Ideally, you have all of this so that CasADi's AD framework can choose whatever is most efficient in a particular situation. There are a lot of other things that comes to it. There are things like ways of calculating the sparse patterns of Jacobians. If you want to have this if you want to export C code, you need rules to export C code, and there are a lot of other things to it. So it's like a very tedious work to try to add new functions, but it's something we are working continuously on. Just like a simple example of how, for example, like an operation such as a matrix product. So CasADi works with chain rules for matrix operations, and in the case of matrix multiplications, you can easily derive rules for what is essentially is a Jacobian times vector product from the left and from the right, and there are references for how to do this. So what about these operations in CasADi? So in comparison to other modeling languages, CasADi has a very rich set of operations, rich set of atomic operations that can be differentiated. So this includes linear system of equations. So you can have like a backslash operation in your modeling code and have CasADi automatically differentiate this to arbitrary order using the chain rule for matrix operations. And we have a number of interfaces solver for this, including a newly added codes for sparse direct LDL factorization and QR factorization with self-contained C code export. So this is part of the CasADi's core, but we also interface to third-party solvers. You can also differentiate nonlinear system of equations in CasADi, and it works essentially by applying the implicit functions theorem. So under regularity conditions, you get these expressions for the derivatives of implicit functions, and this is possible to any order. Importantly, we can differentiate ODE and DAE solvers, and I'm going to return to that in the next page. We have ways of calculating and differentiating matrix exponentials. We can embed and differentiate lookup tables. It's a pretty recent addition to CasADi. If you have, for example, like a lift over drag calculations in an aerospace application or a steam table, you might be able to replace that with a lookup table and think something like into P1, into P2 in MATLAB Octave, and these can be not only evaluated but differentiated analytically to second order in this case. And we have two types of lookup tables implemented. It's a multilinear implementation and B-spline interpolation. these are similar to the codes you have in MATLAB Octave, but with both C code export and ability to calculate derivatives. All right. We also have some support for flow control. So if you have, for example, like a for loop and or an if then else statement, these are typically difficult to embed in a symbolic algebraic modeling framework. CasADi does this by trying to borrow concepts from functional programming languages like Haskell. And there's some support for it. It's something that can certainly be better, but you can do, for example, like a parallel map, and meaning that evaluating a function in parallel. Something that I'm working on currently, it's not yet in CasADi, is being able to differentiate NLP solver objects. So, for example, you take your NLP solver object and say, well, I would like to have the Hessian of the optimal cost with respect to these three parameters. And this is interesting, for example, in parameter estimation, where this has like has the meaning of covariances. So this is something that will hopefully be added in the next version of CasADi. Essentially, being able to calculate parameter sensitivity with one line of code. All right. So I mentioned something about ODE integrators in CasADi. So CasADi works with this pretty general concept of an ODE integrator. So we need a formulation that allows us that works in the context of a source code transformation AD framework, which means that when you differentiate an integrator, we want to be able to differentiate it again and again. And to be able to do this, we work with this DAE formulation that is essentially a DAE going forward in time with initial conditions, coupled to a DAE going backwards in time with terminal conditions. Where the backwards in time DAE has to be linear. The reason why it looks like this is that if you can derive derivatives for this, you can derive sensitivity equations, both forward and adjoint sensitivity equations, and you will see that you end up with a problem of the same structure. So this means that when you create an integrator object in CasADi and differentiate it, even if you use the adjoint mode of algorithmic differentiation, you end up with a problem that with another integrator instance that looks differently, but is still representable in the CasADi's AD framework. All right, so that's about integrators. Well, and so what do you do if everything else fails? Like there are a lot of things that cannot be easily differentiated, and you might have some custom legacy code, and we have been working again, like last couple of years, trying to do as much as we possibly can. Also, in the case when we don't have analytical derivatives. So in the case, or when we cannot break it down into CasADi's symbolic atomic operations, and so to be able to handle like so that's why we added like this support for adding just like being able to add just external functions into CasADi expressions. And there are two ways of adding your own operations in CasADi. There's a low-level API, which is matches that of the C code generation, and then there's a high-level API where you're essentially defining your own classes in MATLAB, Python, and C++, where you're by overloading different methods, you can customize the behavior of this solver object. The main problem with external functions is what to do with derivatives. So one way, of course, is to force a user, or in this case, to write all the derivatives. But it's a tedious and error-prone thing to do. So in the latest version of CasADi, we have also added support for finite differencing algorithms for calculating derivatives for external functions. And I can just mention like how it works. So there are a couple of different schemes, and they attempt to calculate derivatives by automatically selecting the step size that gives you a good trade-off between truncation error and round-off error. And implemented is also a smoothness-seeking scheme where, because often, like in gradient-based optimization, we are trying to calculate derivatives at the end of intervals. So we have a scheme that essentially is a weighted, a linear combination of an upwinded, downwinded, and a central scheme, and then based on the smoothness, it will switch from one to another. So this is something that was added in the latest version of CasADi. So the last thing I want to talk about is structured nonlinear programming. So I talked a little bit about what the kind of NLPs that we get from direct multiple shooting, direct single shooting methods. So they will have this structure. So what does the structure look like? Well, if you look at the Hessian of the Lagrangian, it will typically have some sort of block structure, or if it doesn't have a block structure, you can typically reformulate the problem so that you get a block structure. So this type of structure can typically be solved in the case of direct collocation with solvers such as APMopt. And again, like with in direct collocation, I mean, it's important that you calculate the derivatives exactly, but how fast you calculate often doesn't really matter much, because the difficult part here is typically the linear solver inside in this case APMopt. All right. So, well, can we do better than this? I mean, because if you like with this approach, if you try to go to really hard, like large dimension, you will sooner or later run into bottlenecks. Typically in the linear solver in the for example in APMopt or in other general sparse NLP solvers. And this is even more so the case in the context of direct multiple shooting, because in direct multiple shooting, these blocks here are not only are not just sparse, they are block sparse. So they can be, you can have these dense subblocks here with a lot of non-zeros, and these general sparse linear solvers can be are not very efficient to handle that type of problems. So what is the state of the art to handle that type of problems? Well, the state of the art is to if you look at state of the art code for direct multiple shooting, it's to write tailored solvers that tailor these NLP solution to a particular structure of the optimal control problem. And in direct optimal control, you typically, in one way or another, exploit this band structure that you have in our Hessian of the Lagrangian and Jacobian of the constraints. And this has been implemented in a lot of different codes, both in structured SQP codes, in structured QP codes, and there are also ways like approaches that allow you to project a full space problem into a smaller problem and then solve that efficiently. So these are all these approaches are based on the idea that you tailor the solver code, the NLP solver code, to a particular problem structure. So how do we make these methods available to the CasADi user, where CasADi is this much more general purpose framework that is supposed to work not just with one particular optimal control problem structure, but with any reasonable structure or a wide range of different structures. And basically, we address this with two different approaches. One is to try to detect the block structure, which is typically not too difficult to do. It's a graph. I mean, it's about finding the strongly connected component of a graph. And the second approach which we have been using to address this type of problem is by adding a so-called lift operator in CasADi, which allows you to instruct a symbolic framework to treat an intermediate operation as a variable, as a decision variables in an NLP algorithm. So the codes so that you can do this in CasADi are essentially three codes that allows you to do structure exploiting NLP solution. One is an interface to HPMPC, which is a structured QP method, and then you as a user would have to write your own SQP method around that. Another code is block SQP, which is so CasADi contains a fork of this code, which again where all the block structures are automatically detected by CasADi and then passed on to the solver. And the final approach is this implementation of a lifted Newton SQP, and in this case the idea of the user is to write this single shooting NLP, and then add these lifting instructions that allow you to lift this problem into a higher dimension. And essentially what you do is that you take this problem here, and then these J and G's are taken apart, and we get this set of additional variables that are given explicitly as symbolic expressions. And the problem you're actually solving then in the SQP method is this full space problem where all the Z's here are decision variables. And what you can choose, what you can see is, or what you can show is that this type of problem, this large dimension problem, can actually be solved nearly as cheaply as the reduced space problem. And this was shown in this paper. This is a result that has been known in the context of optimal direct methods for optimal control, but this is extended to this more general purpose structure that you have here. And again, like in because we have lifted to a higher dimension, we can actually now handle things like in unstable systems. We can easily parallelize this. And so this is something that has been implemented in CasADi in this solver called ACPGen. And again, it builds on like the idea that you as a user would have to explicitly identify these Z's. All right. There's like a simple demo of this code. So here it's like it's a parameter estimation example. So I should say the Newton method is especially interesting for parameter estimation problems. Because for parameter estimation problems, your reduced space QP or your reduced space NLP is typically small enough to be solved by general purpose methods. So here's like just a simple. So here's a PDE corresponding to these shallow water equations. You're dropping a drop of water onto a water surface, and we're trying to estimate in this case I think we're trying to estimate the height of the pool in this case, and I think it's the viscosity. And to demonstrate the method, we discretize this on a 100 by 100 grid, So we have so instead of this PD here, we are using, let's say, method of lines to get an ODE with, for each of these components, about 100 by 100. So it's 10,000 times 3, 30,000 ODE states. And then we have these measurements that we're trying to fit this to, and we're going to take 100 steps of leapfrog integrator schemes for each of these measurements. We end up having like in our problem formulations, we have like these 30,000 steps that we have to. So we evaluate this right hand side at 100 points for 30,000 states. So there's a lot of variables in this case, and I should say that for all 100 measurements. So if you want to formulate this as an NLP, you end up with an NLP, a multiple shooting NLP with some 3 million variables and 4 million constraints. Because like in your NLP, we don't have these 100. You only see the measurements. So there's like a dense dependency between the different states. And this, if we were to form the full space QP, we would end up with a problem with some 10 to the power of 11 non-zeros. But with the Newton method, we never have to actually formulate this QP explicitly. We can get we can project this down to a smaller QP while getting the convergence of the full space problem. And in this case, we only have 2 free variables. So our 2 parameters that we try to estimate. So we end up with a QP that we actually a reduced space QP with only 2 variables and about 1 million constraints corresponding to bounds on our height. So you can solve this with CasADi, and then each iteration will take some 35 seconds if you're using a Gauss-Newton approach, or like 4 times longer if you're using an exact Hessian. So this is let's say like a more mainly like a proof of concept code of how you can exploit structure. And so just wrapping up the presentation. So CasADi is a general purpose numerical optimization framework with a strong focus on both online and offline optimal control. It's in particular allows you to do, I mean, either a rapid prototyping of different algorithms, or after you prototype your algorithm, you can export this the solvers, or the derivatives or whatever that you have generated, and export that as self-contained C code. And in particular, this makes it easy. So that's the idea of CasADi, to write a good optimal control problem solvers that can be tailored to your application. And you can do this with different approaches. A lot of CasADi users use a fully disk-type approach, the collocation approach, typically with IPOpt, or you can use a multiple shooting approach. Finally, when you're using shooting type approaches, CasADi provides a very convenient way of automatically calculating sensitivities, as outlined. And then something that is work in progress is to extend this family of structured NLP solvers in CasADi. Just 2 small pieces of advertising here. There's a new book coming out by Jim Rawlings, David Main, and Maurice Steele. It's the 2nd edition of multiple control theory and design, and this new edition is using actually CasADi for almost all of the exercises. So if you're interested in using CasADi for MPC, then you should buy that book from Amazon, and you will learn both. And also, like we recently submitted a new new paper about the CasADi internals. It's quite extensive. It's some 30 pages detailing of how CasADi works internally. So this is a paper it was submitted to Mathematical Programming Computation earlier this year. It's still in review, but if you want to access it, have a look at it, you can use the link here and look at the preprint. So this is probably the best most up-to-date explanation of how CasADi actually works internally, if you're interested in the math behind it. All right. So with that, I want to thank my funding. So I've got my work here in Madison has been sponsored by Johnson Control and by GE Global Research, and I'd be happy to take questions.
Okay, great. Well, thank you for that presentation. And just to ask, what is the pumpkin for?
Oh, I think it's actually like a leftover from presentation I gave during ASDHD, which happened to be during Halloween. Okay. And then I just didn't replace it.
No problem. Well, we're glad to have, I just saw Joris Gillis is on the line as well. He's one of the developers of the CasADi. Do you want to introduce yourself as well? Sorry, you're on mute right now. But we'll go ahead and have some time for questions. We have a little bit of time. If you'd like to unmute your microphone, you could do that, and go ahead and either put your question in the chat window. It just said from Andreas Koda said paper.casadi.org is not accessible right now. So they
oh, okay.
So you might want to check that link. Thanks for that tip. George said no mic is available right now, but anyway, any other questions from the audience? Okay, so here's a question from Andres, page 34, or slide 34. Can you provide a script showing how to implement the structure exploitation algorithm on the example problem by Algebraic?
Yeah, I could pull up the script. I guess I can. I don't know if it's yeah.
Maybe what we could do is if you could just Andres, if you could just email, and then he might be able to send some of that code to you.
Yeah, I mean basically like so the high level explanation is that you take the, I mean, if you look at the example for direct singular shooting in CasADi, it's basically the same thing, and you just add one line of code where you say lift the state. So there's like an operation which says, well, lift, which basically takes two arguments, takes the existing intermediate expression and an initial guess for your for what you're doing. But yeah, there's I can give you a link to that.
Great. So here's another question. There's been a lot of work lately on software packages that build up computational graphs and use automatic differentiation, especially for machine learning, Theano, TensorFlow. How does CasADi compare in CPU performance? Is there any way to leverage some of the work in those communities in CasADi?
So I think that I have not worked with a lot of frameworks from optimal used in the machine learning community. I think like there are some big differences. I think in the machine learning community, typically what you're doing is you're not looking at calculating Jacobians and Hessians. It's mainly about calculating gradients. I think that in performance, I mean CasADi built on a long history of algorithm differentiation codes. I think it's in performance. I don't think there's a big difference. I mean, I guess what in the machine learning community, it's all about maybe about things like parallelization, like evaluating on a GPU. I mean, that's something we can do with CasADi as well, but it hasn't been like the focus in the same way it has been the focus in machine learning. I mean, CasADi is a much more general purpose tool. So in a way, you could probably use CasADi in machine learning applications, and we have seen people actually doing that. But the other way around, you can't really use machine learning tools for the stuff you can do with CasADi, because the type of construct we support is much more general purpose. So yeah, I guess it would be like maybe better to ask that question to someone who has worked with both types of tools.
Great answer there. Okay, so any other questions? We got another one here. What about could you give us an idea of the speed of the pre-processing? So the derivatives look like they're very fast once it's compiled and
right.
In C code form. But could you give us an example of some of the problems that you set up here? What is the pre-processing time to do that code generation, and how long does that take to compile?
So we've really been like focusing on not only fast execution time, but also fast symbolic processing. If you do rapid prototyping, that's very important. And all the graph sorting algorithms that go on in CasADi have a linear time complexity. I think in the case of this parameter estimation example, so this is a very large scale problem. So we're talking about in order of a minute for each iteration of the NLP solver. So I think for that type of for this particular problem, I think setting it up all symbolic processing probably took in the order of maybe 20 seconds. So all the symbolic processing is less than one iteration of the NLP solver in this case. And I think the code so that's without the C code the compilation of the C code. I think the compilation of the C code in this case took something like 4 minutes. So the generation of all the calculation of derivatives and the generation of the C code here took around in total around maybe less than half a minute, and then the compilation 4 minutes, and then each iteration 1 minute.
Okay, that's great. That's very impressive. Well, it looks like we're about out of time now. Thank you for your presentation. Very informative, and it looks like you and others have put in a lot of work into this package. So I just saw that you also had you can do to install for Python, you can do pip install CasADi, which is very nice as well. Right. And it's about a 40 megabyte download. I was just trying that as the presentation was going on. So thanks for making that available as well.
Yeah, and everything that goes on has to do with installation. I need to make a shout out to Joris. He has been doing great work on that domain.
Okay, well, fantastic. Great. So thanks everybody for joining, and I'll go ahead and post a recording of this on YouTube. So if you missed something or want to contact the authors later, there'll be that information on the recording. Okay, well, thanks everybody for joining, and we'll go ahead and sign off now.
All right, thank you.